Today we're talking about something that synthesizes a bunch of things we've been doing so far. We've done conduction, we've done resistance networks, we've done convection now, external and internal flow. Heat exchangers are kind of a synthesis of a lot of the things that we've been talking about all into one problem. So we spend just a few lectures talking about heat exchangers. One, because it is a combination of things we've done, and it's a nice way to wrap up the maybe first two parts of the class before we get to radiation. But it's also something that you're really likely to be exposed to as an engineer doing anything in energy systems. Heat exchangers, as you know, are everywhere. Like they're part of our HVAC systems. They're part of your computer's cooling systems. Anytime you have heat that needs to move from point A to point B or to be removed from a system, almost always you're going to have a heat exchanger. So there's a bunch of different types of heat exchangers. There's maybe two main classifications. The first classification is called direct transfer, and the second is called indirect. And the direct transfer heat exchangers are heat exchangers where you have fluid that's say what we call directly transferring heat to another fluid. And that doesn't mean that the two fluids are coming into contact with each other. It just means that when heat is lost from fluid A, it is transferred directly to a heat sink in fluid B. Okay, so you have in this example up here, we have hot fluid coming in. That's going in the shell side of this, the outer part of it. And then on the inner part of it, you have cold fluid going in. So when heat is transferred from this hot fluid into the cold fluid, it's going across a wall, directly from one fluid to another. So that's called direct transfer. The other type of indirect transfer is something like we show here. This is called a regenerative heat exchanger. It's really common in HVAC. So in, let's say, a large building or even in your home, you would have air that's coming in. You have to replace the air at a certain rate. You can't just let the air circulate. COVID obviously is shown that to be really important. You can't just let the air circulate within the building. You have to replace it at a certain rate. So you're in Wisconsin in the winter taking really cold air from the outdoors and bringing it in at a fixed rate. And then you are also rejecting heat or rejecting, say, stale air that's already been warmed out to the surroundings. So it would be great if we could recover some of that heat from the hot stuff that's going out into the cold stuff that's coming in. And so that's done usually through these regenerative heat exchangers. What this is like a big wheel, maybe of particles or some substrate that's just rotating. Right? And it rotates through the cold air and the hot air streams. The air is forced to go through this porous substrate. And it heats up, this coming in on the hot side, it heats up the substrate to be warm. And then as the wheel rotates around, the cold air is heated up as it goes through on the other side. So you keep the two flows basically separate. But then there's a recovery of the heat that's, most of the heat that's being rejected out through that hot stream going to the surroundings. So these are interesting. I mean, they're used quite a bit, but it's not something we're really going to talk that much about in this class. And what you end up with, by the way, for these is kind of a perpetual transient problem. It's a problem in 1D conduction that you have to solve. That's a non-steady state problem, even though it's the system itself is not really changing. It's an interesting one to solve, but what we're going to talk about. Oh, by the way, on these, just as a side point, you can also incorporate into these other features, like so say you have some microbial scrubbing that you want to do. You can build these things to have microbial scrubbing as part of the system. You can put desiccants in them so they remove or add moisture from one stream to the other. So it's not just heat transfer, sometimes it's heat and mass transfer and other things that are going on. So anyways, the two types that we introduced here, direct and indirect, we're really only going to talk about direct in the next lecture. I kind of have limited writing, at least in the first part today, so follow along. Okay, so when it comes to direct transfer, there's subcategories within that direct transfer heat exchanger. And the subcategories really have to do with how fluid moves relative, one hot fluid moves relative to the other cold fluid. This might be something you've seen before, or should be if you've had heat transfer, as a reminder, there's different types, these different configurations. And the configuration is not just important in how we plumb it up, it's important in how the system thermally behaves, like sort of thermal characteristics of the system. So, for example, let's say we have one way of plumbing up a heat exchanger is shown here, where we have coming in, we have hot fluid coming in on the shell side. Again, this is in this outer region between the outer wall and the inner tube. We have hot fluid coming in here and moving in this direction. I could hook this same device, it's a tube with another tube inside it. I could hook both of them up, so I have hot coming in on this end, cold coming in on this end, and they're both moving in the same direction. The same system. And the temperature profile for that is going to look something like this. We have the hot coming in here, the cold here. So at the moment where they come in, or at the very position where they come in, the delta T across the fluids is really as high as it's going to be. Okay, so you transfer heat according to that rate. As you move along the position, now you're losing heat from the hot, adding heat to the cold. The temperatures start to converge. And that delta T between the two fluids, that's the driving temperature difference for heat transfer that gets smaller and smaller. So eventually your heat transfer from the fluids is kind of decaying as you move along. And as you get to the outlet here, the rate of heat transfer is going to be really pretty low compared to what it was at the inlet. So that's what we call a parallel flow heat exchanger, obviously because the flows are parallel with each other. So you can contrast that to something that is actually more common, which is the counterflow. So a counterflow heat exchanger, you have hot fluid coming in. Now the hot fluid's coming in to the back side here. The cold fluid's still coming in on this side. And the flows are kind of doing this, right? They're crossing each other's paths. So the interesting thing here now is, one, you don't see this kind of exponential decay due to the loss of heat transfer. You actually see that the thermal profiles on either side is pretty linear. It's not exactly linear because the heat transfer is going to correspond to that delta T wherever it is, but it's pretty linear. You're getting a pretty constant heat transfer rate as a function of position. The other thing that's interesting is, over here on this parallel side, the highest that this TC could ever get would be corresponding directly to the amount of heat that's removed from the hot side. So if I drew a line here, the TC could never possibly get hotter than TH out. It's just, you can't do it. Over here, you can have your TC get hotter than your TH out because, you're keeping that delta T kind of constant as you move along and both fluids are adding or removing. So it's really much more common to do the counterflow if you're, unless there's some reason where maybe you don't care about how effective your heat exchanger is, or say one of the fluids has a really high what we call capacitance rate compared to the other, then maybe parallel flow is okay. Or say there's some geometry that's like you have two sources here and your outlet's way over on the other side of the building. It would be really expensive to route it backwards. In that case, maybe you just do the parallel flow, but almost always you're going to want to do something like a counterflow because it's just much more effective. You're getting more heat for the same, right? These are exactly the same tubes here. So it's usually much better to do a counterflow arrangement. So let's really quickly look at some examples here. So this particular example is what a heat exchanger actually looks like. Normally you're not going to just take a tube and put it inside another tube and call that your good heat exchanger. It's not usually done. The geometries are a little more complicated than that. So this over here is called plate frame. So these two over here. So plate frame is a type of heat exchanger where you have a bunch of plates, right? Maybe there are these etched plates or there's little microchannels carved into them. And you just sort of stack them up inside this frame so that the fluid that's coming in, it's a little hard to see, the resolution didn't hold very well, but you have hot fluid coming in this port here. And the hot fluid, if you can maybe squint, you see that there's a groove cut in this part of the channel that allows the flow to move through this hot plate all the way down to be collected at the outlet. And so you have one plate that's like that, and then the next plate has the groove cut on the other side. So the hot fluid actually can't access on the next plate. Only the cold fluid can access here. And then you get the cold fluid going up the other way, coming back out to be collected. So you can take these plates and you just stack them up on top of each other. And the flow ends up being this counterflow arrangement. But if you wanted to add, say, add area to your heat exchanger, you're changing your application to need more power, something like that, you can just take these bolts right here, just unscrew it, pull them out, add plates, and now you have a bigger heat exchanger. As opposed to some of the other geometries that are really fixed. We'll see. So this is a really common one that shows up a lot for different applications. Here's another version over here of kind of the same thing. We have flow coming in. The flow is only able to access channels here, and it sort of has to go up through. You don't see up on the top, there's a similar header. It distributes back, and then the flow goes down and is collected in these channels down here. So just by, let's say, clever arrangement of gaskets and headers, you can force the heat exchanger to do what you want it to do. This is much more common than the stuff that we usually study as textbook type examples. Okay. Here's another really common heat exchanger type that you probably are more familiar with. So if you open your car hood, you'll see in the radiator part of it something that looks maybe like this. Right, so you have air that's coming from driving, or maybe there's a fan pulling through if you're idling. The air is coming in about this direction here, right? And it goes through these little tiny little fins. So you can see the same thing if you look at your air conditioning. You have this these tiny little fins, and the air is forced across this bank of tubes that's running back and forth inside in a arrangement like this. So this is actually called crossflow. Right? And crossflow is different from counterflow and different from parallel flow in that you have fluid that's at 90 degrees. It's like coming in at 90 degrees from the flow for the other channel. So the other flow path. So the thermal behavior of these is actually a little different. It's neither parallel nor counter, but somewhere in between them in terms of its effectiveness. But here, yeah, you see that you have one fluid. Usually it's the air, right? So the air is going to come in here. Air is not a very good heat transfer. It actually kind of sucks. So you have on the air side, the worst side, all the surface area. You've got these fins going into it. You're doing everything you can to extract all the heat and give as much opportunity to extract heat out of that fluid as you can. And then on the other side over here, we have our refrigerant or water or whatever it is. That is actually a pretty good heat transfer fluid. So you just have it going through tubes. It's not limiting the rate of heat transfer, it's the air that's limiting. So this is something you'll see when there's a big mismatch between the, say, thermal quality of the two fluids that are trying to transfer heat.